Okay, so let's just talk through. I'm just going to go through the code really quickly for this particular session that was last week. All right, for those that missed it. All right, so what we're going to do here is we're just going to walk through a bunch of kind of data preparatory techniques as we get ready for machine learning. We're going to move me over here. All right, probably be in the way the whole time. All right, so we're using this serial data set. I'm going to get into the details about it, but needless to say, it's just about kind of ranking various quality of a serials based on a bunch of different factors. Okay, and so when we load in the data, we'll take a look. We've got a bunch of factors here. You see it kind of printed out down here, a bunch of features, about 16 of them. A lot of them are going to need some conversion. All right, so let's take a look at the structure of it real quick, and I'll just whoa, get out of here. Pull this up so we can see it. What we've got here is a bunch of these that are labeled as character. We're probably going to have to change those into factors, and then we have a bunch of numeric values, and some of which probably aren't labeled correctly, like shelf is going to need to be labeled as a factor because shelf is just 1, 2, 3. The weight actually is probably fine. We'll go through that. It might be that vitamins here. It turns out that vitamins is fairly discrete, only has a couple of categories. Anyway, so there's a few of these that we're going to have to work through that are listed as numeric that will need to be characters. Then we also have some factors that are really long that we'll need to condense, all right? But a few, right, using our index here that we identified, all right, I'll just do the index again so we can see it. We know a couple of these right off the bat are going to need to be factors, so we're just going to change them. So the manufacturer is a factor, all right? The type of cereal is a factor, and then we see 12 and 13 vitamins and shelf, probably both going to be factors. So we're just going to use apply, which is a real quick functional, all right, just to convert these over to factors, all right? And then if we go back and we look at our structure again, what we'll see, I can make this big enough, is that these are all converted to factors. So woohoo, all right? So we're working a little bit better. So let's keep going here. We'll take a closer look at manufacturer and type. Right? Manufacturer's got way too many categories. If we look down here on the bottom, if you can see that, we've got, well, not way too many, but anyway, 1, 2, 3, 4, 5, 6, 7 categories, but we just have 2 kind of dominant ones. So what we're going to do is we're going to collapse those down just in its General Mills and Kellogg if you go and look at the data dictionary. So we're just going to convert those, condense them essentially. So let's take a look at this again. So here now we have, right, we just have General Mills, Kellogg, and other. All right, so it's easy, so we just pass other. This works that you just tell you the new value from the old. We actually didn't even have to put these in. We could have just left them there and just added this other, but just makes it a little bit easier to read. So let's take a look at type. Type looks fine. We've just got 2 levels there, 3 levels here. That's totally fine. Weight, all right, so is weight really a continuous variable or a factor level variable? Probably not, right? You have some really kind of discrete numbers here according to weight. So in the future, when we have data come in, it could really be any type of weight. So we want to leave that, I think, just using our instincts there, just as it is. All right, so we've set our variables to their correct class. All right, so now let's keep moving on. The next thing we need to do, and I'm going to skip over some of this because that's a scalar. That's another option to kind of standardize numeric values, but we're going to use a normalizer instead. And so the normalizer is just a min-max normalizer. It's going to put all the data values in a range between 0 and 1. All right, which makes everything computationally more efficient, and it allows us to compare apples to apples, especially for algorithms that have distance measures as a kind of a cornerstone of them, kind of like KNN, which we're going to do next week. All right, so this is just a min-max scalar. If you want to see how this works, it's pretty simple. We're just subtracting, all the values from the minimum value, and then we're getting the range, just dividing it. That's it. All right. So we could do this on a single column, and you can see what the results will look like here. All right. And so if we were to plot the density of this, we can just plot the density of this. That's what it looks like for sodium. All right, that's the unchanged version of it. Okay, and if we were to do the normalized version, voila, what we receive, if you look over here in the lower right, is that the densities are exactly the same, right? It's just that the scale has changed. So all we're doing is scaling the changing the scales and making them kind of on the same level. So now we're going to do that. We're going to do it to all the variables that are numeric in the data set. So we're going to select those names. We're just going to use this names function, which pulls out the column names, and we're going to select if on the serial data set the values that are numeric. And what that does is it just gives us a little list of column names that are numeric. So woohoo, and we can use that as an index. We'll just pass it in here, and voila, we've got all of these values that will now be normalized. So we can take a look at this. Look at str here, again, our structure. Oh, this is looking great, right? So we've got all our values here. Numeric ones are normalized in 0 through 1. We've got our factors that are correctly labeled. So much better, all right? So we're looking good here. We got to keep going. So the next step, and a classical one, is to do one-hot encoding, and that's where, if you're familiar with social science, called dummy variables. So you're going to take those nested factors out of the inside one column. We're just going to spread them out horizontally. So we can do that with this one-hot encoding function. All right. If you want to look at it a little bit more, you take a closer look here. The one caveat is that it wants a data table, which is just a type of data frame. So we're just going to pass it in as data table. Otherwise, one-hot won't do it. We're going to set columns to auto, which will automatically select the columns. All right. Sparsify NAs means that it will drop NA rows. All right. NA columns means that will it take the NAs and make new columns for them. We don't want it to do that, so we're going to tell it not to do that. We are going to tell it to get rid of the NAs. We actually don't have any, so it's not kind of a problem for this. And then it's going to drop columns that are just basically empty, which we don't have any yet either. Okay, so the details of all this are listed inside the package there. It's pretty self-explanatory if you just want to read through it. But basically, all these arguments in here are associated with either having to deal with NAs or what to do if they create a one-hot encoding level that doesn't have any data in it. So the question would be, what do we do with that? And in this example, we say, we want you to drop those. Okay, all right. So here, when we pull this up, what we'll see is that the dimensionality of our data frame has gotten much bigger now, but it actually hasn't gotten any more complex, because all we're doing is pulling out these levels. Okay, so they're already present, but this is much more machine readable. And again, for distance-based algorithms, you have to do this, all right? Otherwise, you wouldn't be able to use these factors inside a, say inside K and N, right? We're all still in the same range from 0 to 1. This just represents the actual presence of it or not, right? And so we can actually see the patterns here. You see there's ones here, there's zeros here because those are not, and there's zeros here, and there's a 1 and zeros up here. Anyway, getting into the details, we just take these levels out and turn them into 1s and 0s, into Boolean values. Okay, so now we're looking really good. All right, the next thing we want to do is just do some simple, so we're going to do create a baseline here for this, but what we have is a continuous target variable. That's the rating, all right, is a continuous variable. What we're going to do is we're actually going to convert that to a factor. We're going to change it to a 0 and 1. All right, so we're going to take the top 75% of the ratings and make that a 1, and anything below that, below 75%, we're going to make that a 0. So we're going to take the top quartile and make that a 1, and everything below that, we're going to make a 0. So we can do this through kind of this 5-number summary. If you look down here, and this is a 5-number summary from Tukey. If you're familiar with a box plot, that's basically just the third quartile right here, the third split. So right here we see anything above 0.33. That's a pretty big space. Actually, most of these are rated pretty high. We're going to be in the 75th quartile. So we're just going to use that number, and we're going to use this cut function here, which allow us to create basically factor level variables. All right. So the way that cut works is that if you want 2 partitions, you have to tell it 3 places to cut. So here, I'm actually going to change this to -1 because we have some 0 values. So you need to tell it where to start. So where the cut function works is you want to start actually in front of where the first value is. Otherwise, it'll pass an NA in there. All right, so it's not necessarily the range of the value, it's just where you want to start. We can change this to -10,000, wouldn't matter. Or you look for the first value inside that range. So here what we're doing is we're cutting on the rating, right? And we're going to add this back in as a factor, or just rating factor. We'll end up dropping the rating value later because it'll be duplicative. But just to show you what it looks like when we compare the two, I left it in. And so here we're going to start at -1. We're going to cut at 0.3 0.43, right? And what this means is that anything between -1 and less than 0.43 will be a 0, and anything above it will be a 1, right? But this is, we're just telling it where to stop because we don't have any values higher than 1. Again, we could change this to a million, doesn't matter. Just telling it where to stop. And then we're just telling it what labels we want. So we want 0 and 1, all right? So we'll just do that. All right, so now we print out and we see we have all these 0s and 1s. If I'll show you just as an example, if we were to change this to 0, and we did it, we would have this 1 NA right here, right? And that's because that value is actually 0. And so again, we just want to get this -1, then we're in good shape. All right. Okay. So, and now we're going to do the prevalence, which is just the percentage of positive values that we have in our data set. All right. So we're just going to table this, and we're going to pull out the second column, and we're going to divide that by the entire length, right? And that will give us our prevalence, which is about 2.7. But all that's doing is just adding up. The table already sums it for us, just adding up all the 1s and dividing it by the entire length of the data frame. So if we did this manually, we get the same thing, right? All right. Here we go. All right, so the next thing we're going to do, we're going to drop some values, and we're going to do some data partitioning and prep for doing machine learning. All right, we're going to get rid of name and rating. Like I said, rating is duplicative, and name is just not going to be useful. Okay, maybe in some more complicated space, we could use NLP methods to make that into a useful feature. But for simplicity's sake, and to be honest, and most likely it won't help, we're just going to drop those two. All right. Now we're going to do some simple data partitioning. We're going to use this create data partition package in Caret. All right. So it's in the Caret package. We don't have to put these colons here, but this is a way if you didn't want to load in the Caret package in particular, you just want to pull out this one function. You can use this double colon here to be able to do that. Okay. And so keeping in mind here, this is the important part, is that we are using the rating value, all right, to do stratified sampling. That will allow us to maintain the distribution of the target variable inside each of the data partitions, right? So maintaining the balance of that target variable, the 1s and 0s, in each one of them. So each one should have about 27% in each of the different partitions in the training, tuning, and testing, right? Super important. Otherwise, we could just have unbalanced data partitions, all right? It just creates an index, all right? So an index is just, if you want to take a look at it, it's just a list of random numbers, right? Just randomly selects those. Well, again, maintaining that stratification, okay? And then what we're going to do, oops, picked on the wrong one here. Then what we're going to do is we're just going to pass that index in, all right? So this is our rows, columns, all right? So we want all the columns, all right? But we only want the specific rows that are created with this partition. And then we're just going to do the opposite, okay? So that creates our tune, and then our that creates our train, and then we have our tune and test set here, all right? So I went over this, but it's a little clunky to create multiple partitions here that have equal balance of percentages. I'm sure there's a way to do it. I just can't figure it out to do it intuitively. And so what we're going to do here is we're just going to run the partition again on this remaining tune and test. We're going to do 50-50 this time because we want our tune and test to be balanced. All right, and then we're just going to pass in that index again here, index as it is, and the negative version of this index, so everything but the items that are listed there. And then what we see is our dimensions for the train are going to be 70%, and then for the tune and the test, down here if you're looking, are going to be 25% and 25%, so they're going to be equally balanced. And then we can check just to make sure that the prevalence did work, that we did the stratification was right. So these are the numbers here that we have from the training set. All right, so actually this should be 40. This changes just a bit, all right? But if we do that, we see it's 2.7. And then here, we've got 8 and 3 again. And so that's also 2.7, which is exactly the same for here. So we have 8 and 3. So that just gives you an example. I'll let you know that the prevalence is maintained throughout these 3 stratified partitions of the data, okay? And that's it. So we've gone through everything here from loading the data in to checking for the classes, collapsing factors. We've one-hot encoded. We coerced things into the right level. And then we went ahead and created our data partitions. One of the things that we didn't do here that's a bigger process, and we'll go into more detail about it this week, is how to deal with missing data. which is always kind of a problem. So there's lots of ways to handle that, and we'll get more in depth into that this week.